Today we are going to look at a new set of identities. We did the sum and difference yesterday. Today we're going to look at double angle identities. These actually are derived right from the sum and difference identities. Let's look at these double angle identities. Now, as I said, they come straight from the sum and difference. You don't need to clutter your notes up with this, but I wanted to kind of throw this in here so you see where these are coming from. Yesterday, we did this sum and difference identity, but we were doing like an alpha and a beta or an X and a Y or whatever it was. They were always different. Well, a double angle would be a scenario where it's taking the sine of 2 times an angle, which I could write as theta plus theta, where these are the same. So yesterday, if I would have had this, I would have run it through my identity, and it would have been sine of the first, cosine of the second, but since they're the same, you end up with sine theta, cosine theta. And it follows up a cosine theta, sine theta, which ultimately is the same because the order that I multiply those doesn't matter. So I end up with 2 of these. And so that's where this is coming from. The sine of a double angle would just be 2 times the sine of theta cosine theta. If you look at the cosine version of it, 2 theta could be changed to theta plus theta, and then we could use our sum and difference identity. It'd be cosine of the first, cosine of the second, opposite sign, and then sine of the first, sine of the second. Well, cosine theta is really just cosine squared theta, and this is just sine squared theta. This is the most common version of it, but sometimes we would prefer it to only have one trig function. Then we could use a Pythagorean identity and replace, like I could replace cosine squared theta with a 1 minus sine squared theta. That's a Pythagorean identity. Then I'd have 1 minus sine squared theta minus sine squared theta, which is 1 minus 2 sine squared theta. And I could do the same thing with the sine squared, and I'd land here. Again, you don't need to be cluttering your notes up. I'm just kind of showing you where these new identities are coming from. But by having them written there, it's going to save us several steps of having to go through the sum and difference identity. Rather than adding the angle to itself, I'm just going to double it, and it's going to hold this relationship every time. And then, of course, here's the one for tangent. Now, let me get rid of all of this so it doesn't look so cluttery. Ultimately, when we have these double angles in a problem right here, the first thing you're going to do is just get rid of the double angle and replace it with its identity. And then after that, we're just going to run through it and do the same thing we've always been doing. I feel like this isn't going to be too tough because you've got that one step at the beginning to replace it, and then we're reviewing. To start with, let's look at one where we have to kind of draw a triangle out. This one says, if sine of theta is 5/13 and it lies in quadrant 2, we want to find all these different double angle relationships. Theta is going to fall in. I'm going to go ahead. It says you can use triangles or identities. I'm going to go ahead and just go back to that triangle method and look at a triangle that's in the second quadrant. Now, ultimately, this is theta. But remember that we use the reference angle when we do these triangles, and I look at what this angle is right here. So let me clean this up a little bit. All right, so in this theta, I'm putting theta right here, opposite over hypotenuse. Hopefully you know that this is a 12, but not just 12, it's a negative 12 because it's quadrant 2. And I'm going to do the sine of 2 theta using this. Like I mentioned, the very first thing you're going to do is get rid of the double angle and replace it with its identity. I'm going to call this 2 sine theta cosine theta. And I'm going to look at my triangle to replace the sine theta and the cosine theta with a fraction. It's going to turn into 2 times. Now I could go to my triangle, but really they gave me sine of theta. I'll just write that. And cosine theta, back to my triangle, cosine would be negative 12/13. And think of your 2 as 2 over 1, and you're just going to multiply that straight across. You have a 10 times negative 12, that's going to be a negative 120. 13 times 13 is 169, and we're just going to leave it there. Now I'm going to show you kind of one time what really did I just figure out here. Well, if I had an angle that was up here in the second quadrant, the sine value of it, I'm saying, is 5/13. That's the sine value. Remember, if I were to double the angle, so instead of going to here, I'm going to double it. I'm going to end up probably somewhere down here if I were to double it, and then find the sine value of that. Well, I'm saying it would equal this right here. It does make sense that it's negative, because if I did double this angle, it would land down here where sine is negative. That's what we're finding when we're doing these double angles, is if I were to have doubled this distance that it went, here's what the value would be. Let's try the cosine. You have 3 options for cosine. I don't care which one we use. To be honest, your best bet is probably to use that second one, and so I'm going to do that because they gave me the sine. I don't even have to look at my triangle. So if I goofed up my triangle, it wouldn't matter. I could still get this one right if I choose to use the version of this identity that only uses the sine. And I can do 1 minus 2. Think of it as a 2 over 1. The sine is 5/13, but I'm going to square that. Now, be sure to do your order of operations. I have to square it before I take it times the 2. I'm going to end up with a 25 times 2, that's a 50, over, and then square your denominator is 169, times the 1, doesn't do anything. Might sneak in here, change my 1 to a 169 over 169, and then I subtract, and I end up with 115 over 169. Notice that it is positive, which makes sense. If I were to have doubled this, I would have landed over here where cosine is positive, but sine is negative. All right, last one. Let's try practicing with the tangent identity. This one's a little bit trickier because it is a fraction. 2 tangent theta over 1 minus tangent squared theta. On this one, I'm back to using my triangle. I'm going to have a 2. Looking at the triangle, the tangent would be opposite over adjacent, negative 5/12. So I'll do negative 5/12 like this. Think of that as a 2 over 1. Now do the denominator. That's going to be a 1 minus the tangent, which again was negative 5/12 squared. Now let's do some cleanup on this. I know that this is going to end up in the denominator. This is going to be a 25 144th. So I'm going to change this to a 144 over 144. Now, I don't have a whole lot of room on these slides, so I'm going to go horizontally. You know, we shouldn't go horizontally. Always go vertical on these. This is going to get me a negative 10 over 12, which I could reduce, but I'm not going to mess with quite yet. Over, I have a 144. Now, this is going to end up going positive because of the squaring, and that's going to leave this then as a minus. So it'll be a 144 minus the 25, because that's going to end up positive. 144 minus 25 gets me a 119. And my denominator is going to be this 144 over, or minus, sorry. Okay, the numerator is going to be 119. The denominator is going to stay 144. Bring that up, multiply by the reciprocal. And here is where I can see that I'm going to be able to do some reducing. This 12 is going to go away, turn that into a 12. I'm pretty sure 119 is prime. I don't think anything else is going to go into that. I'm going to just leave it then. Gosh, really running out of room here. This is terrible. Don't do this on your homework, please. Negative 120 over 119. Now think about what that is. That is really, really close to a negative 1. And when is it that tangent is negative 1? Well, it happens on the 45. So I'm guessing that if I double this angle, I land really, really close to the 45 angle down here in the fourth quadrant. And it does make sense that it is negative. Now, beyond working with the triangle thing, another thing that we've done with these identities is to verify them. This is going to be great practice of 5.1 because I'm going to start off immediately, get rid of the double angle, replace it with its identity, and then we're just going to work on our verifying. Now, before I just copy this right side, did you happen to look at this denominator? What's that look like to you? I'm hoping by now that those Pythagorean identities are jumping out at you and you easily recognize, oh, that's that cosecant squared. That's what that would be from the Pythagorean identity. I'm going to replace that with cosecant squared theta. I kind of like the left side of this better. I'm going to leave it alone and I'm going to work on the right side. First thing I want to do is maybe get rid of the fraction. I'm going to pop this cosine or cosecant guy up and call him sine squared. It's going to look like this, 2 cotangent theta sine squared theta. I like it now because it's not a fraction. However, I'm going to immediately turn it into a fraction because I need both sides to be sines and cosines. So really that's what I'm working on, is getting everything in terms of cosines and sines. And hopefully you see where we're headed here. If you think of those as all over ones, this sine and this squared can go away, and you've got it. They match. Probably should go ahead and swap that around so they truly look like they match. Also, I know it doesn't really matter the order you multiply, but might as well write it so that they do match exactly. All right, so there's another option. We might do some verifying. How about if we try some solving now? That's the third thing. And just like I said earlier, all that's different is you got to get rid of that double angle. I'm looking at this one. Looks like I gave you a sine double angle again. I'm going to rewrite this as cosine x times 2 times cosine x times sine x. I kind of been putting those time signs in there because I want you to recognize that this is not really anything. These multiplications are the same as this one here. You've just got 4 things you're multiplying together. Sometimes if we put parentheses in there as we replace it, we maybe try to distribute or do something crazy, but this is not addition or subtraction. We're just multiplying all this stuff together. I'm going to leave it like that. In fact, I probably can't help myself but to go ahead and rewrite, clean it up a little bit. I'm going to call it a 2, put the 2 in front, call it a cosine squared x and a sine x. And then, yes, it's a minus sine x equals 0, looking to solve in some way, using all of our strategies. I think factoring out a sine x seems like an appropriate thing to do. And I've got 2 cosine squared x minus 1 left. Now, what I like about this now is that this is a single trig function and this has a single trig function. I'm then going to be ready to go ahead and set them each equal to 0. And when I set this one equal to 0, I'm going to end up with a cosine squared x, add the 1, divide by the 2. I'm going to square root both sides. Cosine x is equal to a plus or minus. Do you remember what the square root of 1/2 is? Did that happen to you often enough that you remember? If I just rationalize my denominator here, I end up with a root 2 over a 2, which works beautiful for my unit circle. Now I'm going to solve. Notice it did say in the interval 0 to 2 pi. I'm just going to list each time that it happens. Sine is going to be 0 at 0 and at pi, not at 2 pi, because notice the parenthesis right here, bracket on 0, parenthesis on 2 pi. And cosine is going to be a positive or negative root 2 over 2 at all of the 45s. That's going to be at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And then we're done. Let's try one more of these solving ones, but this one's a little trickier because this 4/7 thing does not look like a unit circle thing. And this isn't a double angle either, to be honest. All I'm really doing is doing a review because this whole thing, when you have to use your calculator solve, gets tricky. And I thought it might be worthy of reviewing that one more time before our test. Again, in the interval 0 to 2 pi, I'm trying to find when, really, there's not a whole lot going on here. I don't have to really rearrange it or anything. I'm just going through that scenario of, oh, I have to go to my calculator on this one. But if I want all the answers from 0 to 2 pi, my calculator is only going to give me one answer. How do I find all the rest? All right, so let's give it a shot. Make sure that your mode is in radian mode. Since it said 0 to 2 pi, that says they want it in radians. And then all I got to do here is do second sine of negative 4/7. And I'm getting a negative 0.61. Now remember what this means. This is an angle in radian measurement. All right, so here it is. It's a negative angle. It's a negative 0.6. Remember that if I were to go this way 1 radian, it's about 57 degrees. So go this way 1 radian, it's 57 degrees. But it's not a full radian, it's only 0.6 of a radian. So I don't know, somewhere like right here, I'm guessing, is what I'm going to have. It's going to go right there. This right here is a negative 0.61 radian measurement. The problem that I have with that answer is that that does not fall within the range I want. I have to, the one we did in class earlier was a tangent, and tangent works nice because they are identical when they're straight across from one another. This one's a sine. They are not the same when they are straight across from one another. Where else would I have an angle with this exact same sine value? Well, it would have to happen over here. Right there is your matching one because they'd have the same, they're both down that same amount, they'd have that same sine measurement. I have to figure out what this angle is, and I have to find out what this angle is in that range 0 to 2 pi. I think the easiest one would be to get the one that's over here. And all I'm going to do is take it because it's sitting in my calculator. This is sitting in my calculator right now. I'm just going to add 2 pi to it. And it's going to go all the way around and land where I want it to land, but it'll be a positive value. I'm going to do that right now. Plus 2 pi. I'm getting an angle measurement of 5.67 radians. I'm just writing this radians because I want you to remember what you're finding is an angle measurement. That's an angle we found. Now I've got to find the matching one over here. And all I really know is that this measurement right here is 0.61 radians. If I want to find this angle, I think I could just take pi plus the 0.61. And that's what I'm going to do. Now, I'd like you to use full values. I don't think it's going to matter too much, but you got to be careful because that full value in your calculator is a negative angle. And really, I'm just using that this space right here is a 0.61 radians. And I'm going to take the pi plus this 0.61 radian. So if you're going to use the full value, you got to make sure you change it to a positive or do something so that it's a positive 0.60824 number. Add pi to that. And I have an angle over here of 3.75 radians. What I have found then is I've solved for x. I have found the two angle measurements. So I don't really want this one because it doesn't fall within the range I want. But these are the two angles that do fall within that range and whose sine value would be this -4/7. Now that definitely worked out differently than tangent, because tangent again was the same when it's straight across. That's easier to deal with. Cosine would work differently as well. You have to understand where, just like I did here, I knew, well, this angle, I would know this angle over here as the matching sine value. You would have to know with cosine, where is its matching cosine value, and draw it out and figure out what to do in regards to pi or 2 pi and adding it or subtracting it based on your picture. Now that was a little review of using your calculator, but ultimately most of your homework here today is going to be on those double angles. So go ahead and jump in and start your homework. Good luck.